Hi everyone, welcome back. In this video we're going to discuss molecular structure, and specifically we're going to explore electronegativity and its trend with the periodic table. We can then use electronegativity differences to determine whether a bond is polar or not. This becomes important because whether or not bonds are polar determines what type of interactions they have with other molecules, and that affects their stability and their reactivity. Let's begin. We talked in previous videos about covalent bonds and how they involve a sharing of electrons between elements. But not all covalent bonds are the same. When nonmetals share electrons, but they do not share them equally, that creates what are called polar bonds. And the unequal sharing of electrons is caused by differences in electronegativity. This image depicts the spectrum of types of bonds, types of polar or nonpolar bonds that we get within our molecules. And we can see that it ranges from nonpolar covalent to polar covalent to ionic. And so while we made a distinction between covalent bonds and ionic bonds in previous videos, it turns out that the phenomenon is actually quite the same. They both involve transfer of electrons, but polar bonds just have an incomplete transfer. So there's a sharing, but it's the electrons are focused on one side of the molecule. And the region of red electron density here, indicated on this right, is high electron density. The blue indicates low electron density. And then the intermediate colors, the green, the yellow, those indicate middle range or intermediate electron density. So in other words, if it's completely green, then that means that the electrons are shared equally. And this only happens when we have bonds between two elements that are identical. For nonpolar covalent, we can also get nonpolar bonds that exist between carbon and hydrogen bonds. And then once we start looking at other molecules that have elements with different electronegativities, then that's going to give us polar covalent type molecules. Electronegativity is what helps us to determine whether or not bonds are polar. It's a measure of an atom's tendency to pull electron density towards itself, and it must be in a molecule. It's similar to when we talked about electron affinity, in that we're talking about electrons going and forming bonds with elements, but in this case, these elements must be in a covalent bond. There's a trend if you take a look at the values, and that is that the electronegativity increases as we go up a column and to the right. And the main reasons for that deal with the effective nuclear charge. If you remember, effective nuclear charge also increases as we go to the right. And so elements with a high effective nuclear charge, like oxygen and fluorine, are going to have a strong pull of electrons towards themselves when they're in the molecules. You do not need to memorize these values, but you do need to understand the trends, that they increase as we go up and to the right. Part of why the elements in the bottom left-hand corner, these metals, have low electronegativities is because if you remember when we talked about Coulomb's law, the energy of attraction is inversely proportional to distance. And so these elements with high numbers of shells have high distances between the nucleus and the valence electrons. And that means that they're not held as tightly. They don't pull on the outer electrons as much. So to summarize, we can say that elements with high electronegativity readily accept electron density, while elements with low electronegativity, or which are called electropositive, they readily give up their electron density. So electronegativity is a measure of how much an element pulls electrons towards it. But if we look at the differences in electronegativity, that's what helps us to predict bond polarity. And bonds with a high enough difference in electronegativity are considered to be polar. You don't need to know these cutoff values, but to be able to rank molecules based on their differences in electronegativity using the trends that we just discussed. So the larger the difference in electronegativity, the more polar the bond, and the larger there will be a partial charge carried by each atom. Bonds exist along a continuum from nonpolar covalent bonds to polar covalent bonds, and then finally to ionic. And this is shown on the graph as the change in electronegativity increases. And if I didn't say this earlier, this is the Greek letter chi. So you might hear me refer to delta chi. As being the difference in electronegativity. So as we mentioned earlier, there are some bonds that have perfectly nonpolar bonds. And those are the case of elements that are bound to each other. In other words, it has to be bound to the same element to have a perfectly nonpolar bond. But for some bonds, like carbon to hydrogen, the value for the change in the difference in electronegativity is fairly small. And this leads to a small, inconsequential partial charge that doesn't significantly affect the properties of the molecule. We'll still classify these as nonpolar, even though they do possess a very small dipole. And you should remember that carbon-hydrogen bonds are considered nonpolar, despite there being a difference in electronegativity. Past that, around a threshold of about 0.4 difference in electronegativity, the size of the dipole becomes large enough to have significant effects on the bond's properties. And this is where we begin to classify bonds as being polar. Nitrogen-hydrogen and oxygen-hydrogen bonds are both examples of polar bonds. The oxygen-hydrogen bond has a higher value of delta chi than the nitrogen-hydrogen bond, and as a consequence, the oxygen-hydrogen bond is more polar than the nitrogen-hydrogen bond. Since the oxygen-hydrogen bond is more polar, then there's larger partial charges that are carried by the oxygen and the hydrogen. And these are depicted by these lowercase delta values, or delta, Greek letter delta, with the positive or the negative charge. So these indicate that there is a partial charge, also known as a dipole. So within these polar bonds, the electrons are attracted towards the more electronegative element, and the arrow points to the more electronegative element. And there's a caveat to that. And that's if you take physics and they look at dipoles, then the bond dipole points the other direction. Let's just write that over again. So, and again, in physics, the convention is to point the arrow away from the electrons. In chemistry, we point it to the electron, the more electronegative element. And above the second threshold, approximately 1.8 delta chi, these atoms tend to completely exchange electrons and form ionic bonds. And there's a large difference in electronegativity between those elements. That's it for this video in terms of the content. Be on the lookout for another video where I go through some examples and allow you some opportunities to practice. Thanks for watching. Bye.